Swayam Prabha. Digital India. Educated India.
Now let us begin with this next module, which is on friction modeling. Okay, so think of a friction. What comes to your mind? Okay, and let us see how this friction can be modeled. See, in the day-to-day life, we experience this phenomena, friction. You have a block lying on the surface, you try to move it, there is some friction resistance that will be felt. You try to move it in the opposite direction, friction is turning into opposite direction. That's a simple thing that everybody has experienced in their life. So what comes to your mind as a simple friction model? Like that, we will start kind of thinking about friction with some common sense understanding and making it a little more deeper and deeper. So let me switch to the slides mode. Okay, and get my pointer also right. Let's see. Yeah, pointer is here. So so that's a model that you have been familiar with probably in your JE mechanics and other kind of courses. Is based on say, okay, friction is equal to mu n. Okay, that's what you say. Okay, now can you represent really in mathematics this friction is equal to mu n? How do you represent it in a mathematical form? Okay, think about it. Write down the equation of friction model. Okay, so while say you have a block that is resting on the surface, and it is applied by some force F, and it is opposed by say some friction force Ff, small f. Then how do you write the dynamics of this system? So now, of course, the additional force Ff needs to be getting considered here. So the F then will be equal to m times acceleration plus this additional force Ff. Now, how do you express this Ff as a mathematical equation? Okay, that is a question. Okay, so now we'll see that different kinds of scenarios here. This is a scenario that we are just talking about. We have a force that is getting applied on the mass m as this F force, and there is a friction as F, and small f is its symbol. And now we want to represent this force. Okay, so we know that as I move the block in this direction, okay, so the block is, if it is moved in one direction, okay, then the friction force is in this direction. If the block gets moved in other direction, then the friction force is in the opposite direction. That is what we know. Now if I say the block moves in this direction, can I capture that intent of that by looking at x? Probably not, because even if I am at some other different x value, I can be moving in the other direction. Okay, I can be at a positive x but moving towards a zero value. Okay, so x may not capture that intent, but x dot may capture that intent, right? Because if x dot is positive, that means I am moving in this direction. My direction of velocity is this. Okay, if x dot is negative, my direction of velocity is opposite. Okay, so let's get pen here. So if x dot is positive, I'm moving in this direction. Okay, oh, I need to change the color of the pen also. So x dot changes, x dot, this is a positive x dot here. Okay, so this x dot is positive here, and then we have this direction of x dot that will be negative. Okay, So the friction will occur in the direction opposite to the direction of x dot. Okay, right? So x dot, if it is moving in this direction, the friction will be in the opposite direction. If x dot is moving in this direction, friction will be opposite to that direction. Okay, so that's how, like, you need to capture the friction in the equation. Okay, and the magnitude of friction, say for simple, when you have this mu n kind of a way of representing the system, typically you say, okay, oh, the friction force here is mu times n. Okay, so that is mu times n only after the block starts moving. Okay, before the block starts moving, friction is equal to this F force. Okay, so we can see, okay, whether that can be also captured in the model. So think about what is that way we can write now the equation for F of F here, F here. Okay, the friction force here. So one can use what kind of a functions, mathematical functions one can use to kind of get this direction, the directionality dependence represented. So if I plot in the with respect to x dot the friction force, then if the friction force is positive value here, okay, as x dot is positive, and then friction force changes its direction and becomes negative as x dot becomes negative, but for any other value of x dot, friction is still remaining the same. That is like a Coulomb friction model. Okay, so this mu n, you say, okay, oh, no matter what is the velocity of x dot, you say, okay, your friction is always mu n. Okay, that's a maximum, like, limiting value of the friction that you consider. We don't consider any dependence on x dot for the friction in our normal kind of a Coulomb friction kind of a model, or normal, like what we have studied in mechanics. I mean the simple JE kind of classes. Okay, so write down this equation. You develop this equation, and then, like, you pause it here and develop this equation, and then, like, see that. So this FF is FC signum of x dot. Okay, so FF will be actually should be negative here. Okay, you can put this sign negative here because it is in the opposite direction to force F here. Okay, so negative of this signum of x dot. So x dot is in this direction, then friction is in the negative direction to x dot. Okay, so that may change this also in the opposite direction, by the way. Okay, so or else, like, you can consider this as a FF, and in the equations you can use negative FF or whatever. So the intent is important here. You can kind of correct little bit nitty-gritties of these equations, but when x dot is a positive direction, then, like, this friction should have a negative direction. Okay, so that's a way you can represent the friction. Oh, sorry, this may not be there because I am considering this, so this is a positive only here, because FF itself is considered in this direction. So that is what is being considered here. Okay, this is already taken care of here, so don't worry about the sign is really positive only here, because I'm actually drawing this force in the negative direction here anyway. So that sign is taken care of because I am kind of, like, representing this force in the opposite direction. So when I'm drawing the free body diagram, that time also I need to have the friction also coming in the similar kind of a direction, then things will be fine. Okay, so that's how things will go. And this FC will be actually your mu c into n. Okay, so this Coulomb friction coefficient of friction will come into picture. Now we want to kind of little bit complicate the matter. Okay, so now we know already that this x dot is also going to affect, like, your friction force, because we know that viscous component we have talked about in the motor model. Okay, that bearing has some viscous friction in it, but typically people normally consider only this viscous part, and, like, they don't consider Coulomb part, because viscous part gives nice x dot relationship. Without this Coulomb component, if x dot, that relationship is linear in nature, it doesn't have this non-linearity. So you see this, like, sudden jump from here to here for the friction as x dot changes is some kind of a nonlinearity in the system. Or if you see in terms of this signum function itself is a nonlinear function. That's why like this becomes a nonlinear equations. So your system becomes nonlinear with these kind of a functions. So again, one can think about what is this friction force. You pause here, again think about and write the equations considering now this viscous part also, and you'll find, you come back to this. So this you'll find now that okay, this friction force is equal to now this Fc signum x dot plus now C x dot. So this is additional component corresponding to the velocity or viscous friction that will get added. Okay, so this is how like you'll represent this Coulomb plus viscous friction kind of a model. Is that sufficient? What do you think? Think about this part. Is this sufficient yet? You see, you have you remember we have done this small, like, and I asked you to kind of take out your mobile and keep it on the surface and apply a force to control. Okay, so when you apply a force, does it start moving immediately, or you feel some stickiness? Okay, especially if you have a cover on your mobile, you'll feel that stickiness with that rubbery kind of a material. So that stickiness comes as an additional kind of a friction part in the model. How do you consider that? It's called stiction. Okay, that is there only to begin with. Okay, once motion starts, then you don't feel that that much resistance. Okay, that is called a stiction or a stickiness in the system. Stiction is a term that is used for that. Okay, so with the stiction addition, how this picture for the model will change? This picture basically, how do you represent stiction in this part? Okay, that you can think about and draw that, and then like you need to see what is a corresponding representation for the equation again. So this is a stiction. So you have momentarily very large kind of a force called Fs coming up here, and then like it decreases suddenly, and you have this again our Coulomb and the viscous friction continue. Okay, so this is like little more enhanced model with the stiction considered. Now again, how do you represent this into, how do you represent stiction now in the mathematical form? Pause again for a while, write your own equations, you create that kind of a space in your mind to understand what is being said here. Otherwise, like you just read these slides or go through this as if you are recording. Go through this recording as if you are just kind of listening to some video. Things may not make sense unless you do some stuff. Okay, so please write down what is that you think as an equation for this case, and then you'll see this equation coming up. Okay, so now this FF will be Fc signum x dot plus Cx dot. That is what we had previously, but that is now only valid for x dot is greater than 0. Okay, it's not valid when x dot is equal to 0. So what that is valid at x dot is equal to 0? What you should represent there. So now x dot is equal to 0, you cannot use signum of x dot, but still there is a change in the sign of this Fs value. Okay, Fs is positive here, Fs is negative here. How do you kind of consider that? Okay, what kind of thing that you can use? Think about this again. See how can you represent that, and then you'll see this. So what you need to do is you need to take F applied here now. See, the system is not moving, but you are applying force. If F applied itself is 0, then again this FF is going to be 0. But if F applied is equal to value which is more, so F applied is 0, then signum of Fs signum of F applied will have some kind of strong a positive value. Okay, so till the time F applied becomes equal to F applied becomes equal to Fs, F applied is what is going to kind of be the friction force. Okay, once F applied becomes equal to Fs, okay, so F applied is equal to Fs, then this friction force will reach its limit value, and things will start moving. Once the motion happens, then you switch from this condition to this condition, and then the friction value is now coming down to suddenly to FC. So that is how this would be represented in the model form. Okay, so till the time F is applied, F applied exceeds Fs value by something, and then the system starts moving, x dot changes its value, then you get into this equation. Before that, you are into this equation. Okay, so F applied has to go beyond Fs to get into this form. Okay, that's what it means. So you see this model representation. So one can simulate this system also, and then check out say a simple system like the mass resting on the surface with this kind of a thing, how the system is going to behave. One can check. Okay, by the way, think about this. In simulation, can you represent it like that and hope to simulate? Do you see any difficulty that may happen here? So think about these issues. They are not very trivial issues. That okay, you may expect some difficulty when there is this kind of a nonlinearity or discontinuousness in the system. It has something to do with some basic conditions that need to be satisfied for the solutions of a differential equation to exist. Okay, so we'll see that. Okay, now again, is this enough? Think about whether this is enough again. Okay, so this captures most of the things, but the main thing that is happening, that this Fs going from suddenly becoming Fc, that is somewhere it's not in the nature, the things are not so sudden. Okay, so for this to understand little more about this, we need to really go into macroscopic level of what is happening into this, how this friction is coming up in the first place, and understand different phenomena that are happening there, and then we can enhance this model further to see that okay, this Fs does not go to Fc in that kind of a sudden fashion here. X is equal to 0 and x is greater than 0, you have some sudden value coming up here. So there is more like a smooth pattern that may be happening here. Okay, so this smoothness that is happening here is the next thing to capture. How this smoothness will come is here. You can see this has at a microscopic level, you can see some differences. That is this is the asperities of this are in contact with each other, undulation or asperities on the surface that engage with each other. And what will happen when the force is applied in the sidewise direction, these asperities on the surface will start deforming, and then they'll start kind of breaking, and at some other point the contacts will happen, or some other point the asperities will start coming up. Okay, so when they move relative to each other, say right now this is a picture of the contacts of asperities that are happening at many different places. As I start moving, this contact will break from these places and it will start making up some other places. Okay, so the contact areas will get deformed to some extent. So this kind of a phenomena that is happening will make that transition to be not so sudden, but it will make that transition to be a little bit smoother. Okay, so this actually also explains this breakage of the contact happens, and then now new contacts come in, again they'll break, again new contacts will come in, again they'll break. That is a kind of a thing that will happen continuously here. But once first time the contacts are broken, that is the highest force that you'll need for breaking the contacts. Next contact is made and immediately it is broken. It is not allowed for the settling of the system to in that contact position. So that's why that force will be little lesser than initial contact breaking force. So that is what you need to see that, and slowly as the velocity increases, you will find this force will come gradually down. Okay, so So this Fs is coming down to Fc is in a gradual manner. So you can conceive some model for that gradual change, and that will typically be based on some experimental observations. Okay, so you get an experimental profile, and then like based on that experimental profile, one can kind of think about this kind of a model. Okay, what kind of model can fit this profile? Okay, so this is an experimental profile. For example, like the Fs will come down to Fc, and then like we'll have this slowly the Coulomb the viscous component of the friction kicking in to kind of get this again higher value. Okay, so this is a kind of a gradual change that will happen in the actual scenario. In some systems, like metal to metal contact, this may not be the key situation. So you need to kind of see these are the situation where is like we talked about in general for the entire model of the friction. Now some phenomena may be dominant in some cases, some phenomena may not be dominant in some cases. Okay, so we need to consider that appropriately. Say for example, in your system, like this friction and Fc will be there, but this change may not be so gradual. Okay, it may be more of a sudden change, also possibility. Okay, so the slope of this coming down here, let me get a pointer, right? The slope of this coming down here may be a very large slope here. Okay, so that may be possibility, and then it will rise again. Okay, in some cases it will come like a very gradually down and then go up. Like that you may have different possibilities depending upon like the surfaces and materials that we are using. But I'm giving you all these different kinds of a model possibility so that one can choose one of these models suiting to the system at hand. Okay, and that's how like one can think about and get appropriate model to appropriate details. You may not be, see, if you are always using motor at a little bit higher speeds, you are not bothered about this part at all. Okay, you are not stopping and starting motor multiple times, and you are not interested in like very fine positioning into the extent. So you see, if you have a positioning system, you will definitely stop, but you are not interested in like fine kind of a positioning, then like you don't worry about this part. Okay, you leave this part to your integrator module to kind of handle if at all. Okay, but if you want to kind of capture these small nitty-gritties, you have these models available, and they'll be useful in the cases when you want to go extremely high precision positioning, considering the friction into account. Okay, but this scenario will not remain for so long, because as a system wears and tears, like these curves are going to shift, or they are going to change. Okay, now you think about this part, like what will happen if this C is very high, and now what is the governing equation for such a kind of a behavior? So then you need to know, okay, what is how gradually you are coming down from Fs to Fc. Okay, whatever that gradually you are coming down, that part will be factored into your equations in some way, and then so you assume say some Gaussian kind of a way of behavior coming down. Okay, so you think about if it is a Gaussian variable, you know the equation of Gaussian curve, or if you don't know, you just Wikipedia में search करो, you'll get the equation of Gaussian curve. Okay, it has some e to the power negative x dot square kind of a relationship in this case coming up, something like that. So if you want to use that kind of a model to go from Fs to Fc, so you are on the part of the Gaussian curve coming down. Okay, we are not worried about a negative part of the Gaussian curve, only positive part of from Fs high value we are coming down with the Gaussian variation to Fc value. That's what we want to do. Then how do you kind of like write the equations of motion, equations of friction here? So think about that. Okay, what is this Ff going to be under such case? Pause, write down your equations and come back. Okay. So what is Ff is coming up here is, you see this some function, additional function that is introduced here is this gx dot. Now this gx dot function will come like get the force from Fs down to Fc value. Okay, and then you have this cx dot come as it is. Okay, and then this gx dot term is given in this fashion. Okay, you have some fc, some kind of a like level constant, it is a shifted kind of a Gaussian thing, and then fs to fc difference is here, like this fs to fc difference, and that is kind of becoming lower and lower as x dot increases. And then vs is a characteristics velocity called Strabeck velocity, that is be used for, this is like a fixed property of the two surfaces, and as this vs is high or low, you will change the slope of this coming down nature. Okay, that's what will happen here. Now again, is there further anything to be considered? Okay, and the answer is yes. If you think of a surface as like a very soft rubber, okay, so very soft rubber, when you are having these two surfaces in contact, like very soft rubber will first have some motion, that rubber will get deformed, kind of a motion will be there, and then like the motion, actual motion of the two surfaces relative to each other, and all this friction and other effects are going to happen. So this deformation that is happening before these other things come into picture is what is missing right now. Okay, one can understand that based on this simple video that is there. So for video I need to get out of these pointer options, I'll leave automatic here, and then you have this video you can observe. So you can see this is a toothbrush which is running on the surface. You need to carefully observe this area. Now the direction is reversed, so the bristles are getting deformed in the other direction, and then they start kind of making and breaking contacts on this paper substrate. Okay, so look at this video carefully. It is moving in this one direction here. You can see that there is some kind of a bristles which are making and breaking contact up here, and then they are kind of when I reverse the direction, they stop, and then unless my deformation happens beyond certain limit, they'll not leave that contact point. Okay, so this is a kind of a phenomena that is going to happen. Okay, when you reverse the direction here, you see that I have some deformation happening without anything happening at this, and in this position, if I leave this brush, okay, if I leave the force, the brush will come back to its original state, because these are cantilever kind of a deformation. They have some stored energy that will push this thing back. Okay, so this is a kind of a phenomena that is going to happen for the cases where you have a very soft surfaces are in contact with a hard surface, for example, and this needs to be getting modeled for a very high precision positioning applications. Okay, so I gave you this example of soft surfaces, but even in the hard surfaces, if you are interested in nanoscale kind of a precision in control, then you will need to have this effect also taken into account. Okay, so that is what is an important thing. Nanoscale is little bit difficult to kind of realize, because there are some uncertainties that will govern this process. But people have developed these kind of models in the literature. You as a mechatronics engineer typically will not have to use this kind of a depth of model. Rather, for a very high precision positioning, more better solutions exist in the form of these compliant mechanisms, or piezo based actuators and things like that. Okay, so we will not use probably this advanced part of the model for the friction, but I mean this is good for you to kind of know, and I'm not expecting you to kind of think about the model for this friction. I'll just give you the model in the next slide to see and think about how people have captured this mathematics in a very elegant way into some of these model equations. This is maybe development a few decades ago kind of a thing. Okay, so this is a model that is called Lou-Gramm model for two universities, Lund University and Grenoble Institute. These two some joint research might have happened, and then this is called Lou-Gramm model of the friction, and it captures all these effects that what we are talked about so far. Okay, and how it captures, and what how these states are defined in this kind of a fashion and all. I mean, it needs a good amount of mathematical, deciphering of things that people have proposed this model. Okay, so we may, I mean, you do that mathematical. I mean, those who are like really intrigued by some kind of a mathematics, this is a challenge for you to kind of really figure out how this is representing what effects, and how this is really the meanings of all these variables are given here. This chi is a friction state which is corresponding to these deformations of the bristles that we showed for the brush, or that kind of a small deformation, and then this corresponding spring stiffness is sigma 0. Okay, in the pre-sliding regime, this sigma 0 is a spring stiffness, and this is a force that will come into picture when you have x dot is equal to 0. Okay, so think about these effects, and this model, how it is capturing what we have said, the intent of these bristol based deformations, and further continuation into normal friction regime, that is sliding regime. So think about that. It is a good food for your brain. Okay, all analytical sharp brains here. So give a nice thought, and understand. If you have any questions, maybe we'll discuss in the discussion session. So we'll end for now here.